Python is a versatile, high-level programming language known for its ease of readability, flexibility, and wide range of applications. Here's a brief overview. Key features: readability and simplicity. Python's syntax is clear and easy to understand, which makes it accessible for beginners. It emphasizes readability, reducing the cost of program maintenance. Clear and understandable syntax. Python's syntax is designed to be clean and straightforward, mimicking natural language to some extent, which makes the code easier to write and read. Example: using indentation to define code blocks instead of braces or keywords. Minimalistic and concise, Python avoids unnecessary syntax, reducing the complexity of the code. Example: list comprehensions provide a concise way to create lists. High-level abstractions. Python provides high-level data structures and abstract concepts that simplify complex tasks. Example: built-in functions and standard libraries handle common tasks without requiring detailed implementation from the programmer. Consistency. The language's design promotes a consistent approach to solving problems, which enhances readability across different projects and codebases. Example: following PEP 8, the Python-style guide, helps maintain consistency in code formatting and style. Extensive documentation and community support. Python's comprehensive documentation and active community forums provide ample resources for learning and troubleshooting, which contributes to the overall simplicity of using the language. Example: the official Python documentation and platforms like Stack Overflow offer solutions and explanations for common issues. Dynamic typing and memory management variables in Python are dynamically typed. Memory management is handled by Python's built-in garbage collector. Dynamic typing. No need for explicit type declarations. Variables in Python do not require explicit type declarations. The type is determined at runtime based on the assigned value. Example: x eder 10 followed by x. Hello is valid in Python, with x dynamically changing its type from an integer to a string. Flexibility in code. Dynamic typing allows for more flexible and concise code, as developers do not need to manage type information explicitly. Example: functions can accept arguments of any type without the need for overloading methods for different types. Type checking at runtime. Late binding. Type checking is performed at runtime, allowing the same variable to hold values of different types at different times. Example: a variable can be reassigned to a value of a different type during program execution without causing a type error. Automatic memory management. Garbage collection. Python uses an automatic garbage collector to manage memory. It reclaims memory occupied by objects that are no longer in use, preventing memory leaks. Example: unreferenced objects are automatically detected and deleted, freeing up memory without explicit deallocation by the programmer. Reference counting. Python employs reference counting as part of its memory management strategy. Each object keeps track of the number of references to it, and when the count drops to 0, the object is deallocated. Example: creating a new reference to an object increments its count, while deleting a reference decrements it, eventually leading to deallocation when no references remain. Memory allocation. Dynamic. Allocation. Memory for variables is allocated dynamically, allowing efficient use of memory resources. Example: lists in Python can grow and shrink dynamically as elements are added or removed, with memory allocation adjusting accordingly. Efficient use of memory. Python optimizes memory usage by internally managing memory for small objects and frequently used data structures. Example: interning of strings, where identical strings are stored only once in memory to save space. Interpreted language. Python is an interpreted language, meaning that code is executed line by line, which aids in debugging. Line-by-line execution. Immediate feedback. Python code is executed line by line, providing immediate feedback on errors or issues. This makes it easier to identify and correct mistakes quickly. Example: syntax errors and exceptions are reported as soon as they occur during execution rather than after compiling the entire program. Easier debugging. The interpreted nature of Python allows developers to test and debug code incrementally, facilitating a more interactive and iterative development process. Example: using interactive shells like IPython or Jupyter Notebooks to run and test small code snippets. Platform independence. Cross-platform compatibility. Python code can be run on any platform with a compatible interpreter, making it highly portable across different operating systems. Example: the same Python script can be executed on Windows, Mac OS, and Linux without modification. No need for compilation. Unlike compiled languages, Python does not require a separate compilation step, reducing the complexity of the build process. Example: running a Python script is as simple as executing pythonscript.py from the command line. Dynamic interpretation. Runtime modifications. Python allows dynamic modifications at runtime, enabling features such as dynamic typing and dynamic loading of modules. Example: importing modules during execution using the ImportLib module, allowing flexible and modular program design. Interactive development. The ability to execute code interactively encourages exploratory programming and rapid prototyping. Example: using the Python REPL read-eval-print loop to experiment with code snippets and test functionalities on the fly. Simplified development process. Reduced development time. The lack of a compilation step and the immediacy of execution contribute to a faster development cycle. Example: making changes to the code and immediately seeing the effects without waiting for compilation. Ease of learning and use. The interpreted nature of Python, combined with its simple syntax, makes it an ideal language for beginners and quick to learn. Example: new programmers can write and run their first Python program within minutes of installation. Efficient use of resources. Lower overhead. Interpreted languages generally have lower overhead in terms of setup and configuration, enabling quicker startup times. Example: setting up a Python development environment typically requires minimal configuration, allowing developers to focus on coding rather than environment setup. On-the-fly execution. Code execution can begin without the need for pre-processing, which is particularly useful for scripting and automation tasks. Example: automating system tasks or data processing pipelines with Python scripts that can be modified and executed immediately. Extensive standard library Python boasts a large standard library that supports many common programming tasks, such as connecting to web servers, reading and modifying files, and more. Comprehensive modules. Wide range of functionalities. Python's standard library includes modules and packages for a wide variety of tasks, from file I/O and system calls to web services and data serialization. Example: the OS module provides functionalities for interacting with the operating system, while the JSON module allows for easy JSON parsing and serialization. Built-in support for common protocols. The standard library includes support for common Internet protocols and formats such as HTTP, FTP, and email handling. Example: the HTTP and URL-lib modules enable web scraping and HTTP requests. Ease of use. Simplified implementation. High-level modules abstract complex implementations, making it easier to perform advanced tasks with minimal code. Example: the SQLite3 module allows for easy integration with SQLite databases without requiring extensive SQL knowledge. Consistent interface. Modules in the standard library often share a consistent interface and naming conventions, reducing the learning curve. Example: functions and methods across different modules follow similar naming patterns and usage conventions. Documentation and examples. Comprehensive documentation. The Python standard library is well documented, with extensive descriptions, usage examples, and guidelines for each module. Example: the official Python documentation, docs.python.org, provides detailed information on each module, including sample code. Community examples and tutorials. The large Python community contributes additional tutorials, examples, and guides, enhancing the usability of the standard library. Example: websites like RealPython and Stack Overflow offer numerous tutorials and Q&A for using standard library modules. Cross-platform consistency. Uniform behavior across platforms. The standard library is designed to work consistently across different operating systems, ensuring code portability. Example: the pathlib module provides a unified interface for file system paths, functioning seamlessly on Windows, macOS, and Linux. Minimal external dependencies. Many standard library modules require no additional installations, reducing dependency issues and simplifying deployment. Example: the random module for generating random numbers and the datetime module for manipulating dates and times are included out of the box. Performance and reliability. Optimized for performance. Many modules in the standard library are implemented in C, offering performance advantages while maintaining Python's ease of use. Example: the re module for regular expressions is implemented in C, providing fast pattern matching capabilities. Maintained and tested. The standard library is maintained by the Python core development team and is subject to rigorous testing, ensuring reliability. Example: regular updates and bug fixes are provided with each Python release, enhancing the stability of standard library modules. Extensible and customizable. Integration with third-party libraries. The standard library provides hooks and interfaces that allow for seamless integration with third-party libraries and frameworks. Example: the logging module can be extended to work with custom log handlers, and the Unitest module can integrate with third-party testing tools. Modular design. Modules in the standard library are designed to be modular, allowing developers to use only the components they need. Example: the collections module provides various specialized data structures like decay and named tuple, which can be used independently. Cross-platform Python is cross-platform and runs on various operating systems, including Windows, macOS, and Linux. Platform independence. Write once, run anywhere. Python code is highly portable and can run on various operating systems without modification, thanks to the consistent behavior of the Python interpreter across platforms. Example: a Python script developed on Windows can be executed on macOS or Linux without any changes. Standard library compatibility. Uniform standard library. Python's standard library provides consistent functionality across different operating systems, abstracting platform-specific details. Example: the OS and Shutil modules offer a unified interface for file and directory operations on all supported platforms. Cross-platform GUI development. Libraries such as tkinter, PIQT, and WXPython allow developers to create graphical user interfaces that work on multiple operating systems. Example: a GUI application built using tkinter will have the same look and feel on Windows, macOS, and Linux. Interoperability with native system calls. Access to system-specific features. Python provides modules that allow for interaction with system-specific features and APIs when needed, enhancing its flexibility. Example: the C types and platform modules enable calling C functions and accessing system-specific information. Conditional code execution. Python allows the inclusion of platform-specific code using conditional statements, ensuring compatibility while leveraging platform-specific features. Example: using if-sys platform Win32 to execute Windows-specific code within a cross-platform application. Development and deployment tools, virtual environments. Python's venv module allows the creation of isolated environments, ensuring that dependencies are consistent across different development and deployment platforms. Example, setting up a virtual environment on both development, Windows, and production, Linux machines to ensure the same package versions are used. Cross-platform build tools. Tools like PyInstaller and cxFreeze facilitate the creation of standalone executables for different operating systems from a single codebase. Example, generating a Windows executable and a macOS application bundle from the same Python script using PyInstaller. Compatibility with various platforms. Wide range of supported systems. Python runs on a diverse set of platforms, including Windows, macOS, Linux, and even less common systems like Raspberry Pi and embedded systems. Example, developing a Python application on a desktop and deploying it to a Raspberry Pi without any modifications. Cloud and web services. Python's compatibility extends to cloud platforms and web services, enabling seamless deployment and scaling. Example, writing Python applications that can be deployed on cloud services like AWS, Google Cloud, and Azure. Community and ecosystem support, extensive documentation and resources. The Python community provides extensive documentation, tutorials, and resources for developing cross-platform applications. Example, official Python documentation and community forums like Stack Overflow offer solutions for cross-platform development challenges. Libraries and frameworks. A wealth of libraries and frameworks support cross-platform development, making it easier to write code that runs consistently across different systems. Example, libraries like NumPy and Pandas are designed to work on all major operating systems, facilitating data analysis tasks regardless of the platform. Common uses. Web development frameworks like Django and Flask facilitate rapid web development. Frameworks for rapid development. Django. Django is a high-level web framework that encourages rapid development and clean, pragmatic design. Example, Django includes built-in features such as an ORM, object relational mapping, authentication, and an admin interface, allowing developers to build robust web applications quickly. Flask. Flask is a micro-framework that provides the essential tools needed to build web applications, offering greater flexibility and simplicity. Example, Flask allows developers to choose components they need, such as templating engines and ORM, providing a lightweight and modular approach to web development. Template engines. Jinja 2. Jinja 2 is a powerful templating engine for Python, commonly used with Flask to generate HTML from templates. Example, using Jinja 2, developers can create reusable templates with dynamic content, simplifying the creation of complex web pages. Django templates. Django comes with its own templating engine, which integrates seamlessly with the rest of the framework. Example, Django templates support template inheritance, making it easy to create a base layout and extend it for different pages. Database integration. ORM support. Both Django and Flask, via SQL Alchemy, provide ORM support, allowing developers to interact with the database using Python objects rather than SQL queries. Example, creating and manipulating database records using Django's ORM without writing SQL statements directly. Migration tools. Django includes a built-in migration system to handle database schema changes, while Flask can use Alembic with SQL Alchemy for the same purpose. Example, applying database migrations in Django with a single command, Python manage.py migrate, ensuring the database schema is up to date. Routing and URL management. URL routing. Both Django and Flask offer powerful URL routing systems to map URLs to view functions or classes. Example, defining URL patterns in Django using the URL's PI file to map URLs to specific views. Dynamic URL handling. Dynamic URL handling allows passing parameters through URLs, enabling the creation of RESTful APIs. Example, defining routes in Flask with dynamic segments. PEM, to handle different resources in a RESTful manner. Security features. Built-in security. Django includes built-in security features such as protection against SQL injection, cross-site scripting, XSS, cross-site request forgery, CSRF, and clickjacking. Example: enabling CSRF protection in Django by default to secure forms against cross-site request forgery attacks. Authentication and authorization. Both Django and Flask provide mechanisms for user authentication and authorization. Example: using Django's authentication framework to manage user logins, permissions, and groups. Extensibility and customization. Middleware. Middleware in Django and Flask allows developers to process requests globally before they reach the view functions. Example: implementing custom middleware in Django to add headers to all responses. Plugins and extensions. Flask supports numerous extensions for adding functionalities such as user authentication, form validation, and database migrations. Example: using Flask WTF for form handling and validation in a Flask application. Development tools. Development servers. Both Django and Flask come with built-in development servers that simplify the testing and debugging process. Example: running a Django development server with the command Python manage py run server to test the application locally. Debugging and logging. Integrated debugging and logging tools help developers identify and resolve issues during development. Example: enabling Flask's built-in debugger to catch and display errors during the development process. Community and ecosystem. Extensive documentation. Both Django and Flask have extensive documentation, providing comprehensive guides, tutorials, and API references. Example: referencing the Django documentation to understand the usage of built-in ORM methods. Active community. A large and active community contributes to a wealth of third-party packages, plugins, and extensions, enhancing the functionality and usability of these frameworks. Example: using community-contributed packages like Django REST framework for building APIs in Django. Data science and machine learning. Libraries such as Pandas, NumPy, SciPy, and scikit-learn are widely used for data manipulation and analysis. TensorFlow and PyTorch are popular for machine learning. Data manipulation and analysis. Pandas. Pandas is a powerful library for data manipulation and analysis, providing data structures like data frames to handle structured data. Example: using Pandas to load, clean, and analyze large data sets with functions for filtering, aggregating, and transforming data. NumPy. NumPy provides support for large multi-dimensional arrays and matrices, along with a collection of mathematical functions to operate on these arrays. Example: performing efficient numerical computations using NumPy's array broadcasting and vectorized operations. Scientific computing. SciPy. SciPy builds on NumPy and provides additional functionality for scientific and technical computing, including modules for optimization, integration, interpolation, and signal processing. Example: using SciPy's optimization module to solve complex mathematical problems in engineering and data science. Matplotlib and Seaborn. Matplotlib is a plotting library for creating static, interactive, and animated visualizations in Python. Seaborn is built on top of Matplotlib and provides a high-level interface for drawing attractive statistical graphics. Example: creating detailed visualizations like histograms, bar charts, and scatter plots to understand data distributions and relationships using Matplotlib and Seaborn. Machine learning libraries. Scikit-learn. Scikit-learn is a comprehensive library for machine learning, offering simple and efficient tools for data mining and data analysis. It supports various machine learning algorithms for classification, regression, clustering, and dimensionality reduction. Example: implementing a machine learning pipeline with scikit-learn to pre-process data, train a model, and evaluate its performance. TensorFlow and Keras. TensorFlow is an end-to-end open-source platform for machine learning. while Keras is a high-level neural networks API that runs on top of TensorFlow. Example: building and training deep learning models for image recognition, natural language processing, and other tasks using TensorFlow and Keras. Data visualization. Plotly and Bokeh. Plotly and Bokeh are libraries for creating interactive and dynamic visualizations that can be easily shared and embedded in web applications. Example: using Plotly to create interactive dashboards with real-time data updates and using Bokeh to create interactive plots and data applications. Dash. Dash is a productive framework for building web applications with Python, particularly suited for data visualization. It's built on top of Flask, Plotly, and React.js. Example: developing a web-based data visualization dashboard with interactive graphs and controls using Dash. Statistical analysis. Stats models. Stats models is a library for estimating and testing statistical models. It provides classes and functions for the estimation of many different statistical models, as well as for conducting hypothesis tests. Example: performing time series analysis, regression analysis, and hypothesis testing using stats models. Big data processing. Dask. Dask is a flexible parallel computing library for analytics that extends the capabilities of pandas and NumPy to larger-than-memory datasets and parallel computing. Example: scaling up data manipulation and analysis workflows to handle larger datasets using Dask's parallel computing capabilities. Apache Spark with PySpark. PySpark is the Python API for Apache Spark, a distributed computing system that can handle big data processing tasks efficiently. Example: performing distributed data processing and machine learning on large datasets using PySpark. Natural language processing, NLP, NLTK, and Spacey. NLTK, Natural Language Toolkit, and Spacey are libraries for natural language processing in Python. NLTK is suitable for research and education, while Spacey is designed for production use. Example: tokenizing, parsing, and performing named entity recognition on text data using NLTK and Spacey. Transformers by Hugging Face. Transformers is a library for state-of-the-art natural language processing using transformer models. Example: using pre-trained models like BERT, GPT-3, and T5 for tasks such as text classification, summarization, and translation with the Transformers library. Reinforcement learning. OpenAI Gym. OpenAI Gym provides environments for developing and comparing reinforcement learning algorithms. Example: training a reinforcement learning agent to play a video game or solve a control problem using environments provided by OpenAI Gym. Stable Baselines 3. Stable Baselines 3 is a set of reliable implementations of reinforcement learning algorithms in Python. Example: implementing advanced reinforcement learning algorithms like PPO, DQN, and A2C for various tasks using Stable Baselines 3. Scripting and automation. Python is often used for writing scripts to automate repetitive tasks. Ease of use and readability. Simple syntax. Python's clear and readable syntax makes it an ideal choice for writing scripts quickly and efficiently. Example: a script to rename files in a directory can be written concisely using Python's OS module. Rapid development. The language's simplicity allows for rapid prototyping and development, enabling quick iteration and testing of scripts. Example: writing a script to automate sending emails using the smtplib module can be done swiftly. Built-in modules, OS and file system operations. Python includes modules like OS, Shutil, and glob for performing various file and directory operations. Example: using the OS module to traverse directories and Shutil to copy and move files. System administration. Modules like subprocess, sys, and platform facilitate system administration tasks, such as running shell commands and managing system information. Example: using sub-process to execute shell commands and capture their output for further processing. Task automation. Scheduling tasks. Libraries like Schedule and Ape Scheduler allow for scheduling and automating tasks at specified intervals. Example, using the Schedule library to run a data backup script every night at midnight. Automating repetitive tasks. Phyton can automate repetitive tasks like data entry, file conversions, and web scraping. Example, using OpenPixel to automate the creation and modification of Excel spreadsheets, web scraping and data extraction. Beautiful Soup and Scrapy. Beautiful Soup and Scrapy are libraries for extracting data from HTML and XML documents. Example, using Beautiful Soup to scrape product information from an e-commerce website. Selenium. Selenium is a tool for automating web browsers, useful for tasks that require interaction with web pages. Example, using Selenium to log into a website, navigate to a specific page, and extract data dynamically loaded by JavaScript. Networking and communication. Automating network tasks. Phyton provides modules like Socket and Paramico for networking tasks such as creating sockets and automating SSH connections. Example, using Paramico to automate tasks on remote servers via SSH. Email automation. Phyton's SMTplib and ImaPlib modules can be used to automate sending and receiving emails. Example, writing a script to automatically send out daily reports via email. Data parsing and processing. Parsing files. Phyton can parse various file formats such as CSV, JSON, and XML using built-in and third-party libraries. Example, using the CSV module to read and process CSV files or JSON module to parse JSON data. Regular expressions. The RE module allows for powerful text processing and pattern matching. Example, using regular expressions to extract specific information from text files or logs. GUI automation. PyAutoGUI. PyAutoGUI is a library for programmatically controlling the mouse and keyboard. Example, writing a script to automate repetitive GUI tasks, such as clicking buttons or filling forms. Automating desktop applications. Libraries like PyWinAuto and AutoPy help in automating interactions with desktop applications. Example, using PyWinAuto to automate interactions with a Windows application for repetitive data entry. Task scheduling and background tasks. Cron jobs and Windows Task Scheduler. Phyton scripts can be scheduled using cron jobs on Unix-like systems or the task scheduler on Windows. Example, scheduling a Phyton script to run at regular intervals using cron on a Linux server. Background services. Phyton can be used to create background services or daemons. Example, using the threading and multiprocessing modules to run tasks in the background. Integration with other tools, APIs and web services. Phyton can interact with APIs and web services to automate data retrieval and processing tasks. Example, using the requests library to interact with REST APIs and automate data retrieval. Database automation. Libraries like SQL Alchemy and PsychoPG2 allow for automating database operations. Example, writing scripts to automate data entry, updates, and queries in a PostgreSQL database. Software development. Phyton can be used to develop desktop applications and games with libraries like tkinter, PyQt, and Pygame. Artificial intelligence. Phyton is extensively used in AI research and development due to its simplicity and the powerful libraries available. Advantages: easy to learn and use, versatile and powerful, strong community support, extensive libraries and frameworks. Disadvantages: slower execution speed compared to compiled languages, not ideal for memory-intensive tasks.